Thank you. Thank you, Antonio. I hope that you can see the screen. Okay, so first of all, thank you for the opportunity to present ALITE. So thank you to EPIC for the organization, and thank you all of you for being connected this afternoon. ALITE is a small company that has been founded quite recently, so at the end of 2020, but it inherits a pretty relevant experience because it comes after the experience of another company that I have co-founded some years earlier and then sold in 2020. It was OPI Photonics. Moreover, since I'm also a professor at Politecnico di Torino, one of the most prestigious Italian technical university, of course, ALITE benefits from strong synergies with my research group at Politecnico. So let's say that ALITE is a sort of the industrial arm of the research activities that we are carrying on at Politecnico. Despite being a young, small company, ALITE is organized into, let's say, teams, or if you want to use high-sounding words, divisions. One working on lasers and the other working on sensing. The one working on lasers will be discussed more in details in the next slides. So let me say just a few words for sensing. The team working on sensing is developing a fiber optic monitoring system. So the entire monitoring system from the sensor itself, typically using fiber Bragg ratings, to the entire interrogation system. But the real keyword that brings together these two teams is the word personalization. We have heard before large companies that are providing off-the-shelf solution, really excellent off-the-shelf solution. In our case, we try to find our niche in customized solutions. So solutions that cannot be found directly on the market for special applications. So, for example, the laser team or laser division is working in providing customized, tailor-made laser sources and bench management devices for processing challenging materials like paper, cardboard, and most important for current application, so-called high reflective materials such as copper, gold, and some kind of polymers. Not only, but also in some direct marking application, like for example in textile, fruits, vegetable. You see in the picture that we wrote apple on an apple. Just this can be of interest, not for welding, but to reduce labels and therefore environmental impact. In practice, what can we do? Well, we can provide customized laser sources. What does it mean? It means, for example, sources emitting in the near infrared with some peculiar feature not easy to find on the market. For example, a customer recently asked us to develop a laser diode emitting at a certain wavelength, and we took commercial diodes. We are not fabricating semiconductors, but working with optics, in particular, introducing the wavelength stabilization, either through external discrete components, and we are also now pioneering the stabilization through gratings inscribed directly into the multimode delivery fiber. We managed to obtain the required wavelength. We are developing blue laser system, and we will see why later on blue is interesting, and also sort of other non-conventional wavelength lasers, like for example, recently a customer asked us to develop a 100-watt fiber laser into L band, so above 1600 nanometers. Moreover, we also develop devices to couple switch and combine high power beams in the kilowatt range. This, I think, is of interest for welding application, because as we know, in welding application, maybe often we have to change the beam, the diameter of beam delivery fiber, so the process fiber. And this can be done by switching between different kind of fibers. Or on the other end, we could be interested into combining different beams to scale the power or to introduce specific features. We heard before about the possibility of using single mode lasers, and we heard that single mode lasers are limited to certain power. Which of course is true. A possible thing to explore could be to combine single mode lasers at slightly different wavelength in a spectral, so therefore in a spectral division multiplexing to scale the power. And we had the opportunity to work with the development of custom devices so far up to 20 kilowatts, but we think that there is still space to increase the performance. But this afternoon, I would like to spend a little more time to present you possible outcomes of 2 European projects in which we are involved that can affect also the welding application, despite these projects are not directly focusing on welding applications. The first project, is an experiment within the Pulsate European project that Antonio mentioned at the beginning. In this experiment, the goal is to develop a compact multi-material additive manufacturing machine, a small one, specific design for artisans' workshop. And being a multi-material means that the machine, with very little change in the configuration, should be able to process different kind of materials, going from high-tech polymers, like, for example, PEK, or highly reflective materials, like, for example, gold, if the artisanal workshop is a jewelry, say. So this means that the machine must be equipped either with a near-infrared source, or if you want to process an highly reflective material with a visible source, like, for example, green, or even better, blue. The role of ALITE is, in this case, in this project, is to both develop the source and to develop the processing head. And we will see in the next slides how these results can be adapted also for more specific welding applications. The other project in which we are involved is called WISE. It's a project that just started recently. And the goal of this project is to develop an all-in-one machine that integrates up to 5 laser processes for the direct fabrication of macro-scale products. And integrating 5 laser processes means that we have, using a single machine, that we have to combine possibly 5 types of lasers together. So we have to combine lasers having different wavelengths. And again, we go to the idea of combining lasers emitting in the infrared and lasers emitting in the visible, again, green, blue. But also lasers operating at different operating regimes. So, for example, in CW for additive manufacturing or for welding, and pulsed for polishing the surface, for smoothing, or for subtracting. So this means that this project requires the development of specific optics, specific what we can call hybrid combiners, to combine all these kind of lasers together. And ALITE roles is in the developing the optical chain, so the entire optical setup from the source to the workpiece. Now, This workshop is dealing with welding application. So how can we use the expertise that we have gained and that we are gaining in working on special projects for welding? Well, in my opinion, the first thing could be into developing hybrid, visible, near-infrared processing heads. This is because, as you can see from the graph that we have here, it's pretty famous in these days because everybody now is talking about the processing of highly reflective materials, copper, which is critical for the electrical transition, gold, etc. And as you all know, these materials are not processed very well with near-infrared fiber lasers, so laser emitting at around 10 something nanometers. So, for example, 1050, 1070 nanometers. And even worse, oh, sorry, even worse, not only those material absorb, oh, come on, poorly absorb at those wavelengths, but even worse, for example, copper, you probably know that changes its absorption depending on the temperature. So when you start the welding process, the absorption is very low, so you increase the power in order to start the melting, then suddenly the absorption increases and this produces vaporization and sputters and in the end a poor quality of the welding or in general of the process. A solution can be to switch to wavelengths that are more absorbed, like for example, in the visible, as you can see from the plot, green or blue. Even better blue than green. However, we have some challenges. Well, infrared and visible light, they are very far apart wavelength. And this poses important challenges to the development of optics, not that much from the point of view of the coating, which can be in any case overcome this limitation, but rather in the performance. If you think of an f-theta lens, for example, that has to produce the same performance in the visible and in the green, if you want to combine these two wavelengths. So another critical thing, if you want to combine the benefit of near-infrared and blue laser light, is that they typically have very different beam quality. In particular, the light coming from the near-infrared fiber laser, as we heard also from the previous talker, the previous speaker, sorry, can be single mode or near single mode. So the M square can be very small. On the other end, especially if you are thinking of blue laser, they come from diodes and with a very poor quality. So the challenge is how can you deal with these two things together? And to solve this challenge, we have developed a new type of processing head that is a patent pending solution implemented to deal with beams having very different quality. And we are currently testing this solution in a new type of a hybrid process in which we can combine the benefit of blue and the infrared. So blue can be, for example, used to increase the temperature, and then you continue the process with the higher quality near infrared. At the moment, the solution is pretty bulky, so it's not as elegant as the picture you see on the upper right part of the slide, but we are working toward that. Another outcome that we expect from our experience that can be used for welding is a derivation of the approach that I was mentioning before for the WISE project, in which we have to combine several types of lasers. So the idea is, for example, that we have to combine together visible or near infrared, or both of them, using the previously mentioned approach, CW beam in the order of hundreds of watts if you are thinking of blue, and probably kilowatts if you are thinking of the infrared, together with a pulsed laser. Pulsed laser that can be in the order of nano to picosecond usually, or at least the kind of application we were targeting was in this range. At the moment, we have developed a prototype of a combiner that can take as an input a fiber with a standard QBH connector coming from the CW laser, while the pulsed laser is delivered in free space. But in the future, we plan to have an all-fiber solution that could be, for example, using hollow core fibers to better deliver the pulsed laser. Of course, an all-fiber solution could be more compact and therefore reduce also the weight of the processing head and improve, therefore, the mechanical performance of the system. And this could be, for example, of interest if one wants to combine welding process with maybe some polishing processes that require pulsed lasers. The question that usually Antonio asks is what can we do for the others, and what the others can do for us is easy to answer. Well, we are a small company, so any help in testing the proposed solution, any cooperation in proposing new technologies, new technological challenges is welcome. And what can we do for the others is to let our expertise in beam shaping and combining to put at the disposal of the others our expertise. So in particular, if you have a non-standard problem for which you need a specific kind of personalization, so you don't find off-the-shelf solution. And this is everything I wanted to say today. So I thank you again for your patience in listening. And if you have any question, I'm happy to answer.